The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Well, let's see. So before we actually start reviewing for the test, I still have to tell you a few small things because I promised to say a few words about what's the difference, more precisely, what's the difference between curl being 0 and a field being a gradient field, and why we had this assumption that our vector field had to be defined everywhere for a field with curl 0 to actually be conservative, for our test for gradient fields to be valid. So more about the validity of Green's theorem and things like that. So we've seen the statement of Green's theorem in two forms. Both of them have to do with comparing a line integral along a closed curve to a double integral over the region inside, enclosed by the curve. So one of them says the line integral for the work done by a vector field along a closed curve, counterclockwise, is equal to the double integral of the curl of the field over the enclosed region. And the other one says the total flux out of the region, so the flux through the curve, is equal to the double integral of divergence of a field in the region. So in both cases, we need the vector field to be defined not only, the left-hand side makes sense if a vector field is just defined on the curve, because it's just a line integral on C. We don't care what happens inside. But for the right-hand side to make sense, and therefore for the equality to make sense, we need the vector field to be defined everywhere inside the region. So I said if there's a point somewhere in here where my vector field is not defined, then it doesn't work. And actually we've seen that example. Oops. So this only works if f and its derivatives are defined everywhere in the region R. Otherwise, we're in trouble. Okay? So we've seen, for example, that if I gave you the vector field minus yi plus xj over x squared plus y squared, so that's the same vector field that was on that problem set a couple of weeks ago, then, well, f is not defined at the origin, but it's defined everywhere else. And wherever it's defined, its curl is 0. I should say everywhere else. And so if we have a closed curve in the plane, well, there's two situations. One is, if it does not enclose the origin, then yes, we can apply Green's theorem, and it will tell us that it's equal to the double integral in here of curl f dA, which will be 0 because this is 0. However, if I have a curve that encloses the origin, let's say like this, for example, then Well, I cannot use the same method because the curl, well, the vector field and its curl are not defined at the origin. And in fact, you know that, ignoring the problem and saying, well, curl is still 0 everywhere would give you the wrong answer because we've seen an example. We've seen that along the unit circle, the total work is 2 pi, not 0. So we can't use green. Or rather, we can't use it directly. So there's an extended version of Green's theorem that tells you the following thing. Well, it tells me that even though I can't do things for just this region enclosed by C prime, I can still do things for the region in between two different curves. Okay, so let me show you what I have in mind. So let's say that I have my curve C prime. Where's my yellow chalk? Oh, here. So I have this curve C prime. And I can't apply Green's theorem to the region inside it. But let's cut out a smaller thing. So let me call that curve. So that one I'm going to make going clockwise. You'll see why. Then I can say, well, sorry, let me change my mind. This lecture is not very well prepared. That's because my writer is on strike. Okay. So let's say we have C prime and C double prime, both going counterclockwise. Then I claim that Green's theorem still applies and tells me that the line integral along C prime minus the line integral along C double prime is equal to the double integral over the region in between. So here now it's this region with a hole of the curl. And, well, in our case, that will turn out to be 0 because curl is 0. Okay, so this doesn't tell us what each of these two line integrals is, but actually tells us that they are equal to each other. And so by computing one, you can see actually that for this vector field, if you take any curve that goes counterclockwise around the origin, you will get 2 pi, no matter what the curve is. So how do you get to this? And why is this not like conceptually a new theorem? Well, just think of the following thing. I'm not going to do it on top of that because it's going to be messy if I draw too many things. But so here I have my C double prime. Here I have C prime. Let me actually make a slit that will connect them to each other like this. Okay. So now if I take, I can form a single closed curve that will enclose all of this region, well, with kind of an infinitely thin slit here, counterclockwise. And so, see, if I go counterclockwise around this region, basically I go counterclockwise along the outer curve, then I go along the slit, then I go clockwise along the inside curve, then back along the slit, and then I'm done. So if I take the line integral along this big curve, consisting of all these pieces, now I can apply Green's theorem to that, because it is a usual counterclockwise curve that goes around a region where my field is well defined. See, I've eliminated the origin from the picture. And so the total line integral for this thing is equal to the integral along C prime, I guess the outer one. Then I need to also have what I do along the inner side. And the inner side is going to be C double prime, but going backwards, because now I'm going clockwise on C prime, so that I'm going counterclockwise around the shaded region. Plus, well, of course, there will be contributions from the line integral along this white segment, but I do it twice, once each way, so they cancel out. So the white segments cancel out. You probably shouldn't, in your notes, write down white segments because probably they're not white on your paper. But hopefully you get the meaning of what I'm trying to say. Okay, so basically that tells you you can still play tricks with Green's theorem when the region has holes in it. Just you have to be careful and somehow subtract some other curve so that together things will work out. There's a similar thing with the divergence theorem, of course, with flux and double integral of div f. You can apply exactly the same argument. Okay, so basically you can apply Green's theorem for a region that has several boundary curves. You just have to be careful that the outer boundary must go counterclockwise. The inner boundary either goes clockwise or you put a minus sign. Okay. And a last cultural note. So a definition. We say that a region in the plane, sorry, I should say a connected region in the plane. So that means connected means it consists of a single piece. Okay, so connected, there's a single piece. These two guys together are not connected, but if I join them, then this is a connected region. We say it's simply connected if any closed curve in it, okay, so I need to give a name to my region, let's say R, any closed curve in R bounds, no, sorry, if the interior of any closed curve in R is also contained in R. So concretely, what does that mean? That means the region R does not have any holes inside it. Okay, so maybe I should draw two pictures to explain what I mean. So this guy here is simply connected, while this guy here is not simply connected, because if I take this curve, that's a curve inside my region, but the piece that it bounds is not actually entirely contained in my region. And so why is that relevant? Well, if you know that your vector field is defined everywhere in a simply connected region, then you don't have to worry about this question of, can I apply Green's theorem to the inside? You know it's automatically okay, because if you have a closed curve, then the vector field is, if the vector field is defined on the curve, it will also be defined inside. Okay, so if the domain of definition of a vector field is defined and differentiable, is simply connected, then we can always apply Green's theorem. Of course, provided that we do it on a curve where the vector field is defined. Otherwise, your line integral doesn't make sense, so there's nothing to compute. But if you have, so again, the argument would be, well, if a vector field is defined on the curve, it's also defined inside, so we're happy. And see, so The problem with that vector field here is precisely that its domain of definition is not simply connected because there's a hole, namely the origin. Okay, so for this guy, domain of definition, which is plane minus the origin, with the origin removed, is not simply connected. And so that's why you have this line integral that makes perfect sense, but you can't apply Green's theorem to it. So now, what does that mean in particular? Well, we've seen this criterion that if the curl of a vector field is 0, and it's defined in the entire plane, then the vector field is conservative and it's a gradient field. And the argument to prove that is precisely to use Green's theorem. So in fact, the correct, the actual optimal statement you can make is if a vector field is defined in a simply connected region and its curl is 0, then it's a gradient field. So let me just write that down for, So the correct statement, the previous one we've seen is also correct, but this one is somehow better and closer to what exactly is needed. If curl F is 0 and the domain of definition where F is defined is simply connected, then F is conservative, and that means also it's a gradient field. That's the same thing. Okay? Any questions on this? No? Okay, some good news. What I've just said here won't come up on the test on Thursday. Okay? Still, it's stuff that you should be aware of, generally speaking, because it will be useful, say, on the next week's problem set. And maybe on the final, it would be, there won't be any really, really complicated things, probably. But there might be some, you might need to be at least vaguely aware of this issue of things being simply connected. Okay. And by the way, this is also like somehow the starting point of topology, which is the branch of math that studies the shapes of regions. So in particular, you can try to distinguish domains in the planes by looking at whether they are simply connected or not, and what kinds of features they have in terms of how you can join points, what kinds of curves exist in them. And since that's the branch of math in which I work, I thought I should tell you a bit about it. Okay. So now back to reviewing for the exam. So I'm going to basically list topics, and if time permits, I will say a few things about problems from practice exam 3B. I'm hoping that you have it or your neighbor has it, or you can somehow get it. Anyway, given time, I'm not sure how much I will say about the problems in there themselves. But, okay. So the main thing to know about this exam is how to set up and evaluate double integrals and line integrals. Okay, if you know how to do these two things, then you're in much better shape than if you don't. And so, oops. So the first thing we've seen, okay, so just to write it down, there's two main objects. And it's kind of important to not confuse them with each other. Okay, there's double integrals over regions of some quantity dA, And the other one is a line integral along a curve of a vector field f.dr or f.nds, depending on whether it's work or flux that we are trying to do. And so we should know how to set up these things and how to evaluate them. And roughly speaking, in this one, you start by drawing a picture of a region, then deciding which way you will integrate it. Could be dx dy, dy dx, rd rd theta. And then you will set up the bounds carefully by slicing it and studying how the bounds for the inner variable depend on the outer variable. So the first topic will be setting up double integrals. And so remember, okay, so maybe I should make this more explicit. We want to draw a picture of R and take slices in the chosen way so that we get an iterated integral. Okay, so let's do just a quick example. So if I look at problem 1 on exam 3B, it says, well, it says to look at the line integral from 0 to 1, line integral from x to 2x of possibly something, but dy dx. And it says, let's look at how we would set this up the other way around by exchanging x and y. So we should get to something that will be the same integral dx dy. I mean, if you have a function of x and y, then it will be the same function. But of course, the bounds change. So how do we exchange the order of integration? Well, the only way to do it consistently is to draw a picture. So let's see. What does this mean? Here it means we integrate from y equals x to y equals 2x, x between 0 and 1. So we should draw a picture. The lower bound for y is y equals x. So let's draw y equals x. That seems to be here. And we'll go up to y equals 2x, which is a line also, but with bigger slope. And then, right, so for each value of x, my region will go from x to 2x. Well, and I do this for all values of x that go from 0 to x equals 1. So I stop at x equals 1, which is here. And then my region is something like this. Okay? So this point here, in case you're wondering, well, when x equals 1, y is 1, and that point here is 1, 2. Okay, any questions about that so far? Okay, so that's the first skill. You know, when you see an integral, how to figure out what it means, how to draw the region. And then there's the converse skill, which is, given the region, how to set up the integral for it. So if we want to set it up instead dx dy, then that means we are going to actually look at the converse question, which is, for a given value of y, what is the range of values of x? Okay, so if we fix y, well, where do we enter the region and where do we leave it? So we seem to enter on this side and we seem to leave on that side. At least that seems to be true for the first few values of y that I choose. But hey, if I take a larger value of y, then I will enter on this side and I will leave on this vertical side, not on that one. So I seem to have two different things going on. Okay, the place where I enter my region is always y equals 2x, which is the same as x equals y over 2. So x seems to always start at y over 2. But where I leave could be either x equals y, or here, x equals 1. And that depends on the value of y. So in fact, I have to break this into two different integrals. I have to treat separately the case where y is between 0 and 1 and between 1 and 2. So what I do in that case is I just make two integrals. So I say both of them start at y over 2, but in the first case, we'll stop at x equals y. In the second case, we'll stop at x equals 1. Okay, and now what are the values of y for each case? Well, the first case is when y is between 0 and 1. The second case is when y is between 1 and 2, which I guess this picture now is completely unreadable, but hopefully you've been following what's been going on, or else you can see it in the solutions to the problem. And so that's our final answer. Okay? Any questions about how to set up double integrals in xy coordinates? No? Okay, who feels comfortable with this kind of problem? Okay, good. I'm happy to see the vast majority. So the bad news is we have to be able to do it not only in xy coordinates, but also in polar coordinates. So when you go to polar coordinates, basically all you have to remember on the side of the integrand is that x becomes r cosine theta, y becomes r sine theta, and dx dy becomes r dr d theta. In terms of how you slice through your region, well, you will be integrating first over r, so that means what you're doing is you're fixing a value of theta, and for that value of theta, you ask yourself, for what range of values of r am I going to be inside my region? So if my region looks like this, then for this value of theta, r would go from 0 to whatever this distance is. And of course, I have to find how this distance depends on theta. And then I will find the extreme values of theta. Now, of course, if the region is really looking like this, then you're not going to do it in polar coordinates. But if it's like a circle or a half circle or things like that, then even if the problem doesn't tell you do it in polar coordinates, you might want to seriously consider it. Okay, so that's, I'm not going to do it, but problem 2 on the practice exam is a good example of doing something in polar coordinates. Okay? So in terms of things that we do with double integrals, there's a few formulas that I'd like you to remember about applications that we've seen of double integrals. So quantities that we can compute with double integrals include things like the area of the region, its mass if it has a density, the average value of some function, for example, the average value of the x and y coordinates, which we call the center of mass, or moments of inertia. So these are just formulas to remember. So for example, the area of a region is the double integral of just dA. If it helps you, 1 dA if you want. You're integrating the function 1. You have to remember formulas for mass, for the average value of a function, say f bar, in particular x bar, y bar, which is the center of mass, and the moment of inertia. Particular, so the polar moment of inertia, which is moment of inertia about the origin. Okay, so that's double integral of x squared plus y squared density dA, but also moments of inertia about the x and y axes, which are given by just taking one of these guys. Don't worry about moment of inertia about an arbitrary line. I won't ask you for moment of inertia about some weird line or something like that. Okay, but these you should know. Now, what if you somehow, on the spur of the moment, you forget what's the formula for moment of inertia? Well, I prefer if you know, but if you have, a complete blank in your memory, there will still be partial credit for setting up the bounds and everything else. Okay, so, the general rule with the exam will be, if you're stuck in a calculation or if you're missing a little piece of a puzzle, try to do as much as you can. In particular, try to at least set up the bounds of the integral. There will be partial credit for that always. So while we're at it about ground rules, how about evaluation? How about evaluating integrals? So once you've set it up, you have to sometimes compute it. Well, first of all, check, just in case the problem says set up but do not evaluate, then don't waste your time evaluating it. If the problem says to compute it, then, you have to compute it. So what kinds of integration techniques do you need to know? So you must know, well, how to integrate the usual functions, like 1 over x or x to the n or exponential, sine, cosine, things like that. Okay, so the usual integrals. You must know what I will call easy trigonometry. Okay, I don't want to give you a complete list. And the more you ask me about which ones are on the list, the more I will add to the list. So, but those that you know that you should know, you should know. Those that you think you shouldn't know, you don't have to know, because I will say, well, of what I will say soon. You should know also substitution. How to set u equals something and then see, oh, this becomes u times du. And so, substitution method. Yes? What do I mean by easy trigonometrics? Well, certainly you should know how to integrate sine. You should know how to integrate cosine. You should be aware that sine squared plus cosine squared simplifies to 1. And you should be aware of general things like that. I would like you to know maybe the double angle, sine 2x and cosine 2x, know what these are. And the kinds of easy things you can do with that. Also things that involve substitution, setting like u equals sine t or u equals cosine t. I mean, let me instead give an example of hard trig that you don't need to know. And then I will answer. Okay, so not needed on Thursday. It doesn't mean that I don't want you to know them. I would love you to know, every single integral formula, but that shouldn't be your top priority. So you don't need to know things like hard trigonometric ones. So let me give you an example. Okay, so if I ask you to, do this one, then actually I will give you, maybe like I will reprint the formula from the notes or something like that. Okay, so that one you don't need to know. Although I would, love if you happen to know it, but if you need it, it will be given to you. So these kinds of things that you cannot compute by any easy method. And integration by parts. I believe that I've successfully test-solved all the problems without doing any single integration by parts. Again, in general, it's something that I would like you to know, but if it shouldn't be your top priority for this week. Okay, so you had a question? Or? Inverse trigonometric functions. Let's say the most easy ones. I would like you to know the easiest inverse trig functions, but not much. Okay? Okay? So be aware that these functions exist, but it's not a top priority. I should say, the more I tell you I don't need you to know, the more your physics and other teachers might complain that, oh, these guys don't know how to integrate. So try not to forget everything. But yes?
For substitution, we have to do the Jacobian,
No. Here I just mean like for evaluating just a single variable integral. I will get to change the variables in Jacobian soon, but I'm thinking of this as a different topic. What I mean by this one is if I'm asking you to integrate, I don't know, what's a good example? 0 to 1 t dt over square root of 1 plus t squared, then you should think of maybe substituting u equals 1 plus t squared, and then it becomes easier. Okay, so this kind of trick. That's what I have in mind here specifically. And again, if you're stuck, in particular, if you hit this dreaded guy and you don't actually have a formula giving you what it is, it means one of two things. One is something's wrong with your solution. The other option is something's wrong with my problem. So, either way, check quickly what you've done, and if you can't find a mistake, then, just move ahead to the next problem. Yes? Which one? This one? Oh, yeah, I mean, if you can do it, if you know how to do it, whichever thing is fair. I mean, generally speaking, give enough evidence that you found the solution by yourself, not like, it didn't somehow come to you by magic. But yeah, I mean, if you know how to integrate this without doing the substitution, that's absolutely fine by me. Just, show enough work. General rule is show enough work that we see that, you knew what you were doing. Okay. Now, another thing we've seen with double integrals is how to do more complicated changes of variables. So, when you want to replace x and y by some variables u and v given by some formulas in terms of x and y. So you need to remember basically how to do them. So you need to remember that the method consists of 3 steps. So one is you have to find the Jacobian. And you can choose to do either this Jacobian or the inverse one, depending on what's easiest given what you're given. You don't have to worry about solving for things the other way around. Just compute one of these Jacobians. And then the rule is that du dv is absolute value of a Jacobian dx dy. So that takes care of dx dy, how to convert that into du dv. The second thing to know is that, well, you need to, of course, substitute any x and y's in the integrand to convert them to u's and v's, so that you have, a valid integrand involving only u and v. And then the last part is setting up the bounds. And you've seen that, probably you've seen on p-sets and an example within lecture that this can be complicated. But now in real life, you do this actually to simplify the integral. So probably the one that will be there on Thursday, if there's a problem about that on Thursday, it will be a situation where the bounds that you get after changing variables are reasonably easy. Okay? I'm not saying that they will be completely obvious necessarily, but it will be a fairly easy situation. So the general method is you look at your region R, and it might have various sides. Then on each side, you ask yourself, what do I know about x and y, and how to convert that in terms of u and v? And maybe you will find that the equation might be just u equals 0, for example, or u equals v, or something like that. And then it's up to you to decide what you want to do, but maybe the easiest usually is to draw a new picture in terms of u and v coordinates of what your region will look like in the new coordinates. And it might be that it will be actually much easier. It should be easier looking than what you started with. Okay? So that's the general idea. There's one change of variable problem on each of the 2 practice exams to give you a feeling for what's realistic. The problem that's on practice exam 3B actually is on the hard side of things, because it's, the question is kind of hidden in a way. So if you look at problem 6, you might find that it's not telling you very clearly what you have to do. That's because it was meant to be the hardest problem on that test. But once you've reduced it to an actual change of variables problem, I expect you to be able to know how to do it. And on practice exam 3A, there's also, I think it's problem 5 on the other practice exam, and that one is actually pretty standard and straightforward. Okay, time to move on, sorry. So we've also seen about line integrals. Okay, so line integrals. So the main thing to know about them, so the line integral for work, which is line integral of f dot dr. So let's say that your vector field has components m and n. So the line integral for work becomes in coordinates integral of m dx plus n dy. While we've also seen line integral for flux. So line integral of f dot n ds becomes the integral along C of, just to make sure that I give it to you correctly. So remember that, I don't want to make the mistake in front of you, you never know. So TDS is dx, dy, and the normal vector, so it's, TDS goes along the curve, and ds goes clockwise perpendicular to the curve. So it's going to be, well, it's going to be dy and negative dx. So you will be integrating negative n dx plus m dy. Okay? See, if you are blanking and don't remember the signs, then you can just draw this picture and make sure that you get it right. So you should know a little bit about geometric interpretation and how to see easily that it's going to be 0 in some cases. But mostly you should know how to compute, set up and compute these things. So what do we do when we are here? Well, here we have both x and y's together, but we want to, because it's a line integral, there should be only one variable. So the important thing to know is we want to reduce everything to a single parameter. Okay, so the evaluation method is always by reducing to a single parameter. So for example, maybe x and y are both functions of some variable t, and then express everything in terms of some integral of some quantity involving t dt. Could be that you will just express everything in terms of x or in terms of y or in terms of some angle or something. It's up to you to choose how to parameterize things. And then when you're there, it's a usual one variable integral with a single variable in there. Okay, so that's the general method of calculation. But we've seen a shortcut for work when we can show that the field is the gradient of a potential. So one thing to know is if the curl of f, which is nx minus my, happens to be 0, well, and now I can say, and the domain is simply connected, or if you want, if the field is defined everywhere, then f is actually a gradient field. So that means, just to make it more concrete, that means we can find a function little f called the potential such that its derivative with respect to x is m and its derivative with respect to y is n. We can solve these two conditions for the same function f simultaneously. And how do we find this function little f? Okay, so that's the same as saying that the field big F is the gradient of little f. And how do we find this function little f? Well, we've seen two methods. One of them involves computing a line integral from the origin to a point in the plane by going first along the x-axis, then vertically. The other method was to first figure out what this one tells us by integrating it with respect to x, and then we differentiate our answer with respect to y, and we compare with that to get the complete answer. Okay, so why is that relevant? Well, first of all, it's relevant in physics, but it's also relevant just to calculation of line integrals, because we've seen the fundamental theorem of calculus for line integrals, which says if we're integrating a gradient field and we know what the potential is, then we just have to, well, the line integral is just the change in value of the potential. Okay, so we take the value of the potential at the starting point. Sorry, we take value of potential at the end point minus the value at the starting point. And that will give us the line integral. Okay. So important, this is only for work. There's no statement like that for flux. Okay, so don't try to apply this in a problem about flux. I mean, usually you'll see, if you look at the practice exams, you'll see it's pretty clear that there's one problem in which you're supposed to do things this way. It's kind of a dead giveaway, but it's probably not too bad. Okay. And the other thing we've seen, so I mentioned it at the beginning, but let me mention it again to conclude things. Green's theorem lets us compute lets us forget, evaluate, find the value of a line integral along a closed curve by reducing it to a double integral. So the one for work says this, and you should remember in there, so C is a closed curve that goes counterclockwise, and R is the region inside. So the way you would, if you had to compute both sides separately, you would do them in extremely different ways, right? This one is a line integral, so you use the method that I explained here, namely you express x and y in terms of a single variable. Say that you're doing a circle, I want to see a theta, I don't want to see an r. R is not a variable, you're on the circle. This one is a double integral. So if you're doing it, say, on a disk, you would have both r and theta if you're using polar coordinates. You would have both x and y. Here you have two variables of integration. Here you should have only one after you parameterize the curve. And the fact that it says curl f, curl f is just nx minus my, is just any, it's just like any function of x and y. Okay, the fact that we called it curl f doesn't change how you compute it. You have first to compute the curl of f. But say you find, I don't know, xy minus x squared. Well, it becomes just the usual double integral of the usual function xy minus x squared. There's nothing special to it because it's a curl. And the other one is the counterpart for flux. So it says this, and remember this is mx plus ny. What's important about these statements is not only remembering, if you just know this formula by heart, you're still in trouble because you need to know what actually the symbols in here mean. So you should remember, what is this line integral and what's the divergence of a field. So, just something to remember. And so I guess I'll let you, figure out practice problems because it's time. But I think that's basically the list of all we've seen, and, well, that should be it.